Hello and welcome to a bonus episode of the natural number game using Lean 4. Today I want to show you something really cool with having to do with instances and classes that I learned about Lean recently and how it applies to the natural number game. Starting us off, I'm going to showcase a few things that are different. First off, to do this stuff with instances, we're going to require mathlib. Mathlib being the math library that defines a bunch of defines a bunch of theorems and lemmas for cool math stuff that a bunch of mathematicians work on. And specifically because within mathlib they use the Blackboard at capital N for natural numbers. There's a bit of a clash, so I switched to using the lowercase n for my nat to avoid that clash with the natural numbers, with the other natural numbers. And specifically, something else I did was inside main.lean, I added a bunch of these imports. That way, when I do lake build, it makes sure to build and compile and test all the theorems. Now, let's see what adding mathlib lets us do. So with mathlib added, let's go back to my nat addition world, and let's see one cool thing that we can do. So one thing we can do with just these lemmas is prove something about our natural numbers, this lowercase n. And then I also had to add namespace mynat, else importing this mathlib.algebra.groups.def would cause a name clash saying that 0add has already been declared in mathlib, we're declaring it here, what's going on. So staying in the namespace mynat avoids that clash. Okay, within mathlib algebra group defs, we have something called an additive monoid. So we're going to want to specify additive monoid, and we're going to want to say that our natural numbers are an instance of that. So this is similar to what we did before, showing that using the instance keyword we can turn our natural numbers into the Lean natural numbers, that we can add our natural numbers, multiply our natural numbers, exponentiate our natural numbers, so on and so forth. Now we're going to show they're an additive monoid, which can help us automate some proofs later on. So mousing over this, we can see an additive monoid is an add semi-group with element 0, such that 0 plus a equals a plus 0 equals a. Well, that's very true about our natural numbers. Specifically, this wants us to provide three things: add a sock, 0 add, and add 0. What is add a sock? Well, that is just we want us to prove that addition is associative. Well, that's what we did right up here. So we can just specify that that's that. And similarly, 0 add is our 0 add above, and add 0 is our add 0 above. And then if I click on this, we go to something within defs.lean, and if I click on this, we go to our proof here. So what's going on? So for an additive monoid, let's look at that first. It says here inside this mathlib file that an additive monoid. What is an additive monoid? An additive monoid is an additive semigroup with an element 0. That's what we saw before. And we can see class additive monoid. It takes m, which is the type, and it says that it extends these two things, and it has some things being proved. So let's go back and see where these lead to. What is add a sock? Where is that from? Well, that's just saying that's from an additive semigroup. Well, we already know that our natural numbers are an instance of the class add, and then we also have a theorem that proves they're associative. We proved that like much early on in the natural number game series with induction. And then here we can see that that's the theorem that we want to prove, and that makes our our stuff, our natural numbers, and add a semigroup. And then 0 add here. Where does that come from? Well, that comes from add 0 class, and this has two things, 0 add and add 0. Let's say, like, adding 0 is means that it's a neutral element, so that we get our element back. 0 is the identity, pretty much. Nice. Okay, so with this we have an additive monoid. Well, what else do we prove in this function? Well, we prove the addition is commutative. So can we have a commutative additive monoid? Yep, we can. And that is add com monoid, where here we only need to prove add com, because we already have these. We already proved it's an additive monoid. If we didn't have these proved, we need to provide fields for all 4. But since we already have this, we just need to prove add com is our add commutative above, and then this add com comes from the fact that, well, an additive commutative monoid is both an additive monoid and an additive commutative semigroup, and that comes from, well, this add com semigroup, which its magma operator has the commutative addition. Nice. So that's a few, like, as they're called, natural number game collectibles. These are a few generalized things that our natural numbers are, or general algebraic structures that our natural numbers can be associated with based on these axioms, or based on these theorems we provide. And these are the axioms of an additive monoid. So that's what we can do with just the addition world. Moving on to the multiplication world, we have a few cool things as well. Initially, just like there's the additive monoid for like addition, we also have monoids and commutative monoids for multiplication, and we can prove that our natural numbers are an instance of commutative monoid. And then we need to make sure we import the right file. If you look around mathlib, you know that you might find that inside the group.defs file, we have this, and then since we add a new import, we need to rebuild our imports. And once that's done, we can see that, nice, this works, and then we need to prove things about multiplication. So mul associative 1 mul mul 1 and mul commutative. And you can see that this mirrors what's going on with add monoid, and add commutative monoid has those same similar 4 theorems we need to prove, and these are some axioms of commutative monoids, and then we can get a regular monoid. Oops. I think does this work? Nice. And so pretty much this is a more general thing, and then in for instance lets us prove something that's less, or this is a more specific thing, because a com monoid is itself a monoid, and so infer instance lets us go simpler. Nice. And then so that's what we have for multiplication. What else can we do with multiplication? Well, we can also prove that with the fact that we have multiplication and addition, and we have how multiplication and addition relate, we can prove something about semirings. So specifically, let's import mathlib.algebra.ring.defs, Do we need to rebuild our imports? Nope. And then we can also instance commutative semi-ring where. Okay. So here we can see that, well, 1 mole, 1 mole 0. I'm not too sure why we need to prove mole 1 twice, even though we did it up here. But we need to prove some other things like left distribution, right distribution. So what is left distrib? So that's saying that for all A, B, C belonging to our lowercase blackboard n, A times B, A times parentheses B plus C equals A times B plus A times C, which we distribute on the left side. Well, that's true, but we call it something else. That is our mole add up here. Mole add, and similarly we have right distrib with add mole. Then I wonder if I comment these out, how many more things I have to prove. Similar amount. Okay. And then 0 mole is just, I think we called 0 mole. Similarly for mole 0 is called mole 0. The fact that mole is associative is mole associative. Mole commutative is mole commutative. And 1 mole, 1 mole, mole 1, mole 1. I think the reason that this doesn't inherit some of the stuff from here is because, well, you can see here this is a semi-ring and a commutative monoid. The commutative monoid provides some information, and then the semi-ring provides other information. Commutative semi-ring. This is a semi-ring and a commutative monoid. Try to prove a semi-ring first. What would we need? I think some of these. This is extra. That's it. Okay. Yeah, potentially. Not too sure why it doesn't know some of the other stuff, but I'm guessing because this has maybe a monoid with 0 and some other information, it goes through a different path. Regardless, here we have proof that we're a commutative semi-ring, and that is a very powerful thing indeed. Before we go to our last couple of instances, there's one cool thing I want to show you with the simp tactic. So remember in our multiplication rule we did something pretty complex like mole left commutative with a bunch of rewrites and a reflexive equality. Well, we can use the computer to automate some of this stuff. So for example, if we have something like A, B, C, D, E, all of these are our natural numbers, and we want to prove that A times B times C times D, all that times E is equal to C times B times E times A times D. Well, one way we can do that is with something called the simplify tactic. The simplify tactic uses lemmas and hypotheses to simplify the main goal, target, or non-dependent hypotheses, and it has a bunch of variants. And so here we can see simp made no progress because we haven't tagged anything as we haven't tagged anything with simp. And so there are a few ways we can do this. One, we can arbitrarily list out attribute simp and add that to, say, mole associative. Still doesn't work, but here simp made some progress, which is cool to see. You can see that we got to some sort of from here to here, some sort of ordering, and it made some progress. You can kind of see that like left justified all the parentheses. We can also tag things like lemmas directly with simp, like this. And then simp. Let's see if we've tagged enough for this to work. Yep, it worked, but how did it work? Well, we can use something like the simp question mark, and it'll give us a hint. Try this. And I think if I click this, oops, it'll reset it, and it says, okay, simp only by repeating these two hypotheses. So by combining mole commutative and mole left commutative, we get to where we want. And we can see, okay, what does mole commutative kind of get us? It goes from it made no progress. What about just mole commutative? Made some progress, and both them together, mole left commutative, get us to solve this complicated expression. Nice. And then let's move on to the inequality world. And let's import something from mathlib for some partial and some preorders and some partial orders. Import mathlib dot init dot order dot defs. Now we need to rebuild our imports, and let's add an instance pre-order where, well, for this we need less than or equal reflexive and less than or equal transitive. Refl we have, and less than or equal transitive we also have. Oops. And you can see that these, a pre-order is reflexive, transitive with some of these things defined, and then we have the reflexive and the transitive, and then this extends LE and LT, which we already defined. And then here it says LT should be defined as a function A to B. It says A is less than or equal to B, or not, or and not B is less than or equal to A. Nice. And then we also have partial order. And what is that? Well, a partial order is reflexive, transitive, and asymmetric relation on less than or equal to. And we can see that it extends a pre-order by adding anti-symmetry. Less than anti-symmetric, anti-symmetric, less than anti-symmetric. Oh, spelled this wrong up here. Symmetric, anti-symmetric. And then here we have our partial order. Nice. So quick recap. In this episode, we added mathlib to our natural numbers. And why did we add mathlib? To get access to a whole bunch of cool instances like monoids, semirings, and partial orders and pre-orders. In addition, we can use simp to solve complicated stuff, and then we added something to main.lean. So if this file compiles, everything is fine, and similarly lake build tests everything. Hope you enjoyed this bonus episode.